quantity depending on the temperature and oscillations. And also we use a K-type thermocouple in this characterization. The sample mass that we used in this situation was approximately 2 micrograms, and the sample temperature, of course, the same from room temperature of about 1.8 Kelvin. Now, let's then look at the characterization by the X-ray diffraction. We find that in our X-ray diffraction, we've got 4 peaks that were visible. So we've got the 110, 200, 211, and the 220, which are characteristic of a BCC phase structure. But we also find the existence of a phase, which is what I was talking about, the A15 phase. Now, this is related to that part or that peak there, a rather small one, and that one, it determines what type of phase or the type of material we're dealing with. So it's BCC, but some percentage of it refers to a specific type of BCC structures, which is the A15 phase. Now, we also that this A15 phase occurs at around 36 degrees in terms of the true theta, and we also find that from this characterization, we see that there are no impurities which were detected in the sense that we don't have any shifts from the already recorded crystal structures in literature for this specific element that we're dealing with. Now, we also that I also put there just to see what we mean by the BCC structure, which is that situation there, by using the Vespa software, where we made MO the base, since it was the biggest percentage of our structure. So we used that to develop that BCC structure that we see there, and the literature, of course. Now, the largest parameters were also calculated, and the crystallite size was also calculated. Now, we found that using that equation there, which relates to the Miller indices, we find that we've got a lattice parameter of approximately 3.19 angstroms. This also agrees with literature, which is, of course, that value, the 3.13 in terms of the literature. And of course, the space group for these type of elements that we're dealing with is that which is given over there. Now, we also went on to find, of course, the crystalline size, as I said, but the method that we used, we applied the Schur equation. There may be issues related to this equation, but of course, for the purpose of demonstration, in terms of the crystalline size, we used this to characterize, and we used that as the equation, the Schur equation, and from this, we found that the value that we got was about 300.58 angstrom, which if one converts to nanometers, is about 30 nanometers, and that also is in agreement with literature, or rather already studied literature on this material that they're dealing with. And of course, I provided again the references for some of those. Now, we then go on to the resistivity as a function of temperature measurements that we've done. We find that in this situation, there is a normal metallic behavior observed when one comes from about room temperature down to about 10 Kelvin, in the sense that there are no weird anomalies that are happening in this situation. So that's the normal metallic behavior. And once we do that, this is consistent with studies that have been done for A15 structures, in that there happens to be a transition from the normal state, where one would have normally gotten a residual resistivity, but we don't get it with superconducting, so we transition from the normal state to superconducting state. And this sharp transition is what has been observed, and it is in line with what theory predicts for A15 structures. Because BCC structures alone tend to have a rather gradual transition. So it wouldn't be a sharp one, but it would be a rather gradual transition from normal to superconducting state. Now, in terms of the different applied fields that we used about from 0 to about 0.7 Teslas, and in all those situations, we tend to say there's a shift of these superconducting transitions towards the 0 Kelvin there. And this means that when one applies the magnetic field to our structures, we tend to have that the superconducting transition tends to be affected by the applied magnetic field, in a sense that it decreases. Now, the superconducting transitions with an increase, of course, tend to go towards 0, which is the shift that I've mentioned. And apart from the superconducting transitions that we have there are no abnormalities related to the structural, magnetic, or change in density transitions that we observe for this alloy that we're dealing with. Now, from that data, we can then also try to find out what is the critical magnetic field in terms of the superconducting transitions. So since we're changing the applied magnetic field, on our x-axis we have that, and then on our y-axis we've got what was changing as a result of that, which is the superconducting transitions. However, for us to correctly fit that equation there, we have to go to what the Ginsburg theory, Ginsburg line of theory predicts. And from that, we have to change the graph in the axis such that we then have that the y-axis becomes the applied field and the superconducting transition is over there. And from this, we can then extrapolate what was the upper critical field for this material that we're dealing with. And of course, the equation that you get is this one in a general term, where HC2, which appears there, is about the upper critical field with temperature, and A and B, which you see there, are just parameters to adjust how the data fits. And of course, we've got that at a transient temperature of 0 Kelvin, which is somewhere there, we've got a maximum of the upper critical fluid, and the maximum upper critical fluid is the absolute 0. Now, we also have that a few more definitions with regard to the formula itself. At that superconducting transitions, we've got that the upper critical fluid becomes 0, which is there, and the suppression of superconductivity occurs at that position. So I won't go into much detail with regards to this. Now we'll then go on to specific heat measurements with regard or relative to temperature measurements. So in this situation, we find that again we've got an effect of magnetic field on the superconducting transition, and the decrease has been observed with regards to this dip. So in a normal situation when there's no superconductivity, in other words, no pairing of copper pairs in our alloy, they will not have a